Hello and welcome to Automata, Grammars, and Computability. This is video 2, so we will be talking about deterministic finite automata. Now, to talk about finite automata, which today we'll talk about deterministic, but there's also non-deterministic, we'll have to talk about finite state machines. So, what's the difference between a finite state machine and a finite automaton? I'll use an example of a vending machine. Usually a state machine, as you may have seen them before, has a loose set of rules. It does have to do with what the input of something is, what its state is, and what its output is. So looking at this vending machine, the input could be coins, and it also could be the selection, right? So you're going to put these things in, and the machine actually has the ability to count up how much money you've put in there and whether you have enough for a particular snack. So basically, the machine keeps this state that has the snack selected and the current amount. So then it will be able to either give you the snack and give you change, or it might say that it's insufficient. So right now, even though I've described a vending machine, it's still a little bit vague as to how exactly the states and selections work, what coins are allowed, what the snacks are. So this is very loose as is. So when we model something in computer science, it tends to be quite complicated. Sometimes it's fun, but because of all of the parts that go into it and the fact that algorithms can be pretty brittle, we need to be quite careful as to what those states are and what the outputs are. So a little bit more picky than I had with the vending machine before. Now, besides these particular computer science related examples, it is possible to use finite automata to model real world stuff as well. Let's look at a real world example of a turnstile, which is a little bit simpler than a vending machine. Now, because the turnstile is simpler than the vending machine, we can actually draw something a little bit more rigorous associated to it that represents the states and transitions. So the state of this turnstile can be locked, and you can try to push it, but it's just not going to do anything. And then if you put in a coin, the machine will become unlocked. You can actually go ahead and keep looping and trying to add more and more coins. And in this case, the turnstile is just not going to do anything more. It's just going to remain unlocked. So you're not going to get change from this machine. But the second you push that turnstile when it's unlocked, it will become locked again. And hopefully you make your way through. So because the turnstile is simpler than the vending machine, it's easier to draw these kinds of diagrams and think about what the states, transitions, and what the maybe output is. So that's what we're going to be doing, is we're going to be drawing these circles and arrows to represent various languages. With all that said, let's go ahead and draw finite automata. Now, a finite automaton is a very specific thing. So let me break down what those diagrams look like. A finite automata diagram is going to have circles. Circles represent states, and we also should have a double circle that indicates a final state, as in when the input is done, that's where it's going to end up. So for example, here's something more math specific. Here are these three states. I have Q1, Q2, and then Q3, which has a double circle, which means that's a final state. Now that you have those states, you are going to draw arrows. Arrows are going to be labeled with one or more symbols. So here I have these arrows that are labeled 0 and 1. And specifically, I have a 0 that Q1 has pointing into itself, then 1 that points from Q1 to Q2, 0 which points from Q2 back to Q1, then Q2 to Q3 with 1, and Q3 has 0, 1 that loops back in on itself. Finally, well, at the beginning, we also need a way to start our input, which is going to be that there's going to be a start state that is shown using an arrow that comes from no other state. So in this case, I'm going to point into Q1 directly to indicate that that is the start state. Great. So that's the breakdown of what the pieces of the drawing are, but I haven't really talked about what it means yet. So just to reiterate, a finite automaton is a very specific thing. It consists of states, which in this case is Q1, Q2, and Q3. It has transitions, which are these arrows that go between the states. It has a start state, which is an arrow going into a state coming from nowhere else that we can see. We have an accept state. In this case, just one. You can have more than one, but it's represented by a double circle, right? So this represents the pieces of the finite automaton, so we know what to draw, but let's talk about what it actually means. I want to pause for a moment here to remind you about recognizing a language. A finite machine M recognizes a language A if A is equal to the set W such that M accepts W, right? So one way to represent a language is with strings over an alphabet, and you can create a machine that represents those words that it should accept. Another way to write this is to say that A is equal to L of M. L means language. So when I talked about machines previously, I didn't actually define what I meant by that. It turns out that the machines that I was thinking about that recognize languages were these finite automata, right? So this is one way to talk about whether a string is in a set or not. Basically, this finite automata is going to take in an input of a finite string, and it will output accept or reject. This finite string is over an alphabet. So looking at our example from before, this is something that takes in elements over a alphabet of zeros and ones. And if you just follow through on these transitions, you can decide whether a particular string in the alphabet is accepted or not. We'll run over an example in a moment here. In general, the computation process is begin at the start state, read input symbols, follow the corresponding transitions, accept if you end with the accept state, and reject otherwise. So as promised, let's look at two examples. I have here 0, 1, 1, 0, 1, which is going to be accept. So basically what's going to happen is this 0 is going to be read in, and at that point, you are going to see 1, 1, which means, by the way, that this is being consumed, and it's going to end up in Q3. Because I saw these two 1s in a row, which took me out of Q1, I end up in Q3, and then it doesn't really matter what happens after that because Q3 loops in on itself, so you know that it's going to accept. On the other hand, for this other example, I have 0, 0, and so that's going to loop in on Q1. Okay, that's fine. And now I'm going to have 1, 0. So 1 takes me to Q2, which is great. I mean, I'm getting closer to the accept state, but 0 takes me away. At which point I have 1, which lands me in Q2 again. And since I did not end up in Q3, this is going to be a reject. I recommend pausing the video and trying to think about what other examples of strings this finite automata will recognize, and see if you can come up with a description of what the language is. So the machine M1 accepts exactly those strings in A, where A is equal to W, such that W contains a substring 1, 1. And that follows because you can see that we follow from Q1 to Q3 by having 1, 1, at which point you never escape. But if you only see a single 1, it's always going to take you back to Q1. Good. So let's do some more examples to get a better intuition of what's going on. So let's look at this example, which has the states S1, S2. It has transitions of A and B. The start state, of course, has the arrow pointing into it, and the accept state has the double circle. And I want you to take a moment to think about what language does this DFA accept. In this case, the answer will not be provided in the video. Okay, so moving on, let's look at one more example. In this example, I only have one state, which I have called Q0. The transition is just the letter A, and the start state and the accept state are actually the same in this case, right? So I have a start state, but the start state happens to be the accept state. So again, take a moment and try and think to write a set notation of what language this DFA accepts. Now that we have an intuition of what these DFAs are supposed to look like and what finite automata mean, let's formalize the definition in terms of math. So a finite automaton is defined as a 5-tuple, which I'm writing as Q, sigma, delta, Q0, and F. Right? So this tuple is just a grouping of a couple of different items that put all together is what you need to be able to define a finite automata formally. Q represents the states. So we saw before Q1, Q2, Q3, and those little circles are going to represent those states. Capital sigma represents the finite set of alphabet symbols, which you've seen before as 0, 1, or A and B. It can be anything. Delta represents the transition function. So delta is from Q cross sigma to Q. And these are the arrows that are drawn on the DFA. So when you write DQA equals R, it means it goes from state Q, and it consumes the letter A, and it goes into state R. Q0 is the start state, and F is the set of accept states. So I guess it's better to start numbering from 0. I've been using different letters, sometimes Q1, sometimes S1, but if you just use the variables that are defined here and start counting from 0, then Q0 is going to be the start state, the thing that takes in that arrow and doesn't come from anywhere. And F is going to be the set of accept states, so basically those double circles. So these are normally the letters that are used, as you can see throughout the examples that we've had in our slides. There has been a variety of different letters that I've used, but they're just variables, so as long as it's clear, I don't super care what you use. Now that we have talked about the formal definition of finite automata, we can go back and look at those definitions that I had for strings and languages and put that notation back in. So a string is a finite sequence of alphabet symbols, which is going to be a set sigma. So sigma represents those alphabet symbols. A language A is a set of strings over an alphabet. In other words, A is contained in sigma star, where star means that you can repeat the letters in sigma and pick different ones over some finite length string. And then the length of a string n is the number of symbols in it, which is usually going to be n, which will be n is greater than or equal to 0. So basically, you're going to take the letters in sigma, and then you're going to grab some of them, and you can put them together. And now you can hopefully have a machine that represents what it means to consume each of those letters in turn, and then decide whether it's accepted or rejected in that language. A couple more vocabulary terms here. The empty string epsilon is the string of length 0, and the empty language, which is like the circle with a slash through it, empty set, is the set with no strings. So then more formally, with recognizing a language, a machine M accepts the string W is equal to W1, W2 up to Wn for each Wi in sigma if there is a sequence of states R0, R1, R2 up to Rn in Q, where R0 is the start state, which is Q0. Ri is equal to delta of Ri minus 1, comma Wi for I is greater than or equal to 1 and less than or equal to n. And then finally, if Rn is in F. So this takes the diagram that we had before, and it describes specifically what it means with that mathematical language, what it means to accept or reject a string. Another thing that you'll notice here is I switched the variables up on you again, so I have R's and W's here. So again, hopefully this makes sense, and it's okay to see different kinds of variables and letters and alphabets throughout. The last part of this video is just an example that I recommend you work out on your own. You can pause the video. But I want you to draw a DFA where 3 consecutive heads coin tosses is accepted. Your solution should reject any other sequence of results. So you can't have less than 3 coin flips. You can't have more than 3 coin flips. So just it has to be exactly 3. And then another thing that you can do as follow-up is change your solution to accept any sequence of coin tosses that contains 3 consecutive heads. So notice here that the first part of this problem is basically only going to accept one particular string, which is of length 3, and it consists of 3 consecutive heads coin tosses. So here is the first part of the solution to the first coin flip problem. So because I'm only accepting 3 heads in a row, I'm going to have state 1, 2, 3, and 4, which is only going to go H, 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 and then in state 4, it's going to accept. And then, of course, I need to think about what's going to happen if I have more coin tosses, which is I need another state, and I need to basically go there if I see any tails. So what you'll see here is that from 1, if I have a tail, I'm going to go immediately to fail, and also from 2 and also from 3. And the difference is that going from 4 is that if you see H, 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 but then you see anything after than that, that's also going to take you to this fail state. And then after that, it will just loop in, right? So this accepts exactly 3 heads in a row, not more, not less. That's it. And then the other part of this problem, which is to accept anything that takes that contains a sequence of 3, I will leave as an exercise for you. All right, that's it for now. Thanks for watching.